Okay, let's start. Hello. My name is Jan Pöschko, and together with Marlon Chetman and John Pacey, we'll talk about cloud platform support for Wolfram Documents now. We've already heard some of these things in the two keynotes on Monday, so some of this will be repetitive maybe, but we'll try to go into more detail and just show you some features that work on the web in the cloud platform. And of course, there will be room for questions in the end. So we're already on the cloud here. You can see the interface of the Wolfram Universal Cloud Platform. It has a file explorer over here, so you have access to your notebooks and documents in your Wolfram Cloud storage. You can open them, you can create new ones. There is a documentation center that works just like the ordinary Mathematica documentation. And then there is this huge wide area for the notebook interface. And the idea is that this really should work very much like the ordinary Mathematica notebook. So you can see there are cells, there are cell groups, cells with different styles. We have a title here, sections, and so on. So this should all be quite familiar. And we spent particularly much effort on getting the editor to work right. So as you can see here, I can place the cursor here and I can just start typing, right? And I can do evaluations using Shift-Enter like in ordinary Mathematica, create new cells, and so on. And so the editor itself, we spent some time working on syntax coloring, for example. That's very helpful for Wolfram language code. So you can see you have a module here with a local variable inside it, and then some table with another local variable. They're all styled differently. Then there's another symbol that's not defined yet, so it gets another color and so on. So that's everything we're used to from desktop Mathematica should work in the cloud as well. Also, when you assign a variable a value, it changes its color to black, for example. So these are all the little details we had to care for on the web, of course. Same for formatting. So it's like a WYSIWYG editor on the web. You can select text and open the formatting palette, quite similar to desktop Mathematica as well, and then just apply some styling and it will just work. There's also an insert palette where you can insert special characters, although we'll still improve this a little bit, and hyperlinks. So you want to create a link here, you just say hyperlink, and then you can insert this one. So that's the ordinary way how you interact with these notebooks. And then particularly useful and certainly appreciated by a lot of people is the code assist features in desktop Mathematica. So we also spent a lot of effort in trying to replicate these features on the web. The most basic variant of this is symbol completion. So if you start typing here, it will suggest symbols that start with whatever you typed. And it's quite intelligent about this, so it will suggest more commonly used symbols more prominently. It's also sophisticated in a sense that when you, let's say you solve, and so it's aware of where in the expression you are with your cursor. So here, if we are in the first argument of solve, and for example, it will suggest integrate here as one of the suggestions. Let's just put something here. Whereas now I'm at the position inside solve where options could be supplied. Right? There's no way I can supply an option to solve in the first argument, but then in the third argument it makes sense. So now when I type IN here, it will actually suggest options to solve. And that's very helpful if you don't remember the thousands of symbols that are in the Wolfram language. Obviously I forgot something here. So we get the result. So that's symbol completions. Quite similar are function templates. So let's say you start typing and then you choose a symbol or you open the square bracket, you get this little down arrow down here, and you can activate it by pressing enter, and it will show you some templates. So these are the function signatures of the symbol you just type. If I select one of these, it will pre-populate the cell with templates. I can fill it out by pressing a tab. And so that's also quite helpful. Also similar character completion. So if you just press escape and start typing, it will show you characters that are possible. Same for \bracket, for example. And as you can see, all these characters actually work on the web. It also wasn't quite trivial to do because you have to integrate the Mathematica font into the browser, but so that just works. So there are a lot of details we have to take care of for something like this to work on the web. And I think we made some really good progress, but of course there are a lot of things that haven't been done yet. So, for example, all the output cells are by default at least still images. That's just because it works very well and you're guaranteed to get something that looks right. And replicating all the sophisticated typesetting in the front end, to do that on the web would be really hard. So we're working on it, but we're not quite there yet. So when you have such an image, you could save that image to your desktop, but it's not something you could make selections in or something like that. So there are certain limitations, but we got pretty far already. And if you think that all was easy, then you're probably not involved in web development. But otherwise, I still hope you appreciate how that works. In a rather experimental stage is still the predictive interface, but we're really working on that as well. I think especially for new users to Mathematica or the Wolfram language in general, that's really useful. So if we load that package and do some computation, it should come up after a while. So you get these suggestions in the suggestions bar. You can click them, and it will do the right thing. Right, but there are many small details we still have to work on, but we're making good progress. So that's pretty much all about I want to say about the editor for now. And now Marlon will continue with very exciting support for manipulates on the web.
Thanks a lot, Jan. I appreciate that help. So as Jan suggested earlier, that we're trying to get everything in Mathematica into the cloud platform. That obviously he spoke about notebooks, and now we're trying to do the same for manipulates. Oh, sorry. Thank you. Sorry about that. I'll just hold it. All right, can everybody hear me now? All right, great. Sorry about that. I wasn't sure how this was going to work out. But in any case, I've been working on Manipulate, and we've been trying to gain greater support for it, considering it's one of Mathematica's commonly used features. We've gained some great support for the fundamental controls, and we've made great segue on that. So currently we have Manipulate. As you can see here, this is a text input field. It currently just has a regular string here, but it obviously demonstrates that if we were to just take the D off and evaluate it, you can see the change functionality. So that suggests that we now have input fields working in manipulates. If I go further, this is a bit of a more interesting example. Here we use Google Maps. Now, obviously it's in a browser, but we're not using the browser technology to do this. We're using the Mathematica interface of HTTP client, and we're using URL fetch in particular, though. So if you look at this example, we're making an HTTP request to the Google Static Map API, and we're interfacing with it through Manipulate, actually. Oh, boy. I don't know what happened there. But in any case, we'll try to work off of that. And as you see, I'm zooming in. Okay, I don't know what's the problem with that. Sorry about that, guys. But apparently it's jumping. But as you can see, though, outside of that we're currently using a button set and input field, and we're using a vertical slider on the side. So this is showing and demonstrating that we now have the ability to traverse between different control types. So all in one setting of a manipulate, which is very similar to how Mathematica currently operates. So if I scroll down to another one, here is just another simple example of a manipulate here. where we just, okay, that's just really weird, just jumping. I'm just going to evaluate that real quick. Sorry about that, guys. As you can see, we're just using the basic slider control here. We're just using the subscript functionality, and it's increasing the subscript of X into a triangulation here. This example here is demonstrating the power of just whatever you can do and manipulate this here. I'm going to evaluate it because I saw some weird behavior earlier. Cellular automatons, so as you can see, okay, sorry about that. We're transforming it geometrically, and these are just various transformations we're making. And this is, again, just sliders, nothing too impressive about that so far. And this is about the same here. I'm going to evaluate that as well, just play it safe, because apparently something strange is going on here. All right, and that's just a simple example. But this case here is another example of sliders where we have a clock. We demonstrate the use of changing time and hours and minutes and seconds. And here you see we're changing the clock hands around. And that's a nice example. Here, from here on, I'm showing you an example of how to change the different control types. So as you see here, I have a setter bar that's showing cosine, sine, and cotangent. And nothing too special about that. But what I am demonstrating is the ability to change between control types. So as you can see, that's a pop-up menu at the bottom, and this is a setter bar at the top. So if you notice, I just changed the option right here. And it's essentially the same manipulate, but I'm able to change between the controls very easily. And the interface is obviously the same for the most part outside of just like one individual control. Here, I'm able to also, as Mathematica can do, change between the control type and turn it into a slider. So I have a slider that was initially meant to be a setter bar that can actually interact as a slider. So just as you can in Mathematica, obviously. Nothing too impressive, but it does demonstrate the power of changing control types. And here we have a slider 2D example where we also change the control type as well, but this also demonstrates the power of independent controls on one variable, that is. So as you see, I have one here of a slider, which obviously is meant to be a 2D case, and I have a two-dimensional slider control form. So if you notice that both sliders change and update correctly, and they appear to work the same way. It's just that here's the X values and here are the Y values. And this is just how Mathematica functions. So you're seeing the exact same behavior as you would in Mathematica, actually. And we're moving the point around with the circle. Here's another example of just a battery gauge. I'm sorry about this mic. Apparently I'm not holding it up straight. But in any case, here we're just demonstrating how we can change the setter bar as well as the slider. This was not too special either, but it just again demonstrates the slider 2D functionality, as you can see here. It's just a simple parametric plot that's skewing in certain directions, depending on the axis you build it off of. And here we demonstrate some basic functionality of checkbox, and again, sliders again, but as you see, the frame's no longer there, and if I click it again, it is there. So again, I'm just beating across the head of the ideas of you initially had with manipulates already in Mathematica, but we're now demonstrating them in the browser technology. So you're now seeing both manipulates in the browser and as well as Mathematica. Now, the only drawback is that you don't get the continuous action built in yet. So you have to constantly wait for the server to return you the data back. So that's a bit of a drawback, but we're working on that functionality to make it synchronous. So that way you can await the output as you deal with the control. And it's not waiting for the server to do what it's supposed to do. Here I'm demonstrating some styling mechanisms. We have just a manipulate style box here and various row and all kind of various other styling mechanisms and annotations that deal with controls. But nothing too spectacular here. We're just showing that we can handle styles now. And I also demonstrate the use of turning the option panel to false here. So that's nothing too spectacular, but again, just showing and demonstrating the power of the manipulates and options and how we can interface with them. And here's another example. This one's showing how you can kind of style and place your controls a certain way in the layout of manipulate. So as you notice here, we have a slider that deals with the amount of rows displayed, as well as columns with M. And as you can see, it's very responsive, and it adjusts the layout properly as it does in Mathematica. And here we have another case of we're just dealing with a slider, and we're interfacing with the graphics of whatever the spherical plot is projecting on the screen. And we're able to manipulate the sliders just as we would in Mathematica. Nothing too different here. And the same for this case here. As you can see, this again demonstrates the power of 2D sliders, and at the same time shows you some layout features we now have built into the cloud platform and Wolfram Documents. Okay, and same for this one as well. And as you notice too, we also have the frame labels built in this example, where we have the ability to label an axis if you want to, or anything, and manipulate just as Mathematica does with the frame label option, as you can see right here. So we're able to demonstrate where the top, the bottom, the left, the right sides are inside of the layout. And that's pretty neat, I thought, to show you guys. So you're seeing that we're getting closer and closer to the functionality that Mathematica presents to you. And here is just a simple cone with a plane intersecting. Nothing too special, but it does show the heavy computational ability we do have in the cloud, and we can now handle very heavy computations now within a short time span. But in general, we support various control forms and controls, and we're getting more and more every day. So currently, we just have the fundamental controls of manipulate, but as you can see, it's constantly growing and growing. So I'm going to defer to John Pacey. He's going to speak to you about graphics so he can answer your question more directly.
Yeah, that was a good question, Tally. So as you could see in all of these manipulates, the output is image by default. It's actually rather close to working with 2D and 3D graphics, so that you could do that. So you could actually rotate the 3D graphic inside there. But again, that's something we're working on. So as Marlon pointed out, I'm John Pacey, and I do everything graphics related in the cloud platform, which is, as John has alluded to, pretty complicated and hard. Okay, so how does 2D and 3D graphics work in the cloud platform? So basically, we need to re-implement, at the very least, a low-level drawing layer in JavaScript. For 2D, it's SVG currently, and in 3D, it's WebGL. Okay, and how it's implemented is as a modular extension to the cloud platform. So there's a Mathematica package that kind of interfaces between the Mathematica graphics language and, in this case, my JavaScript drawing layer. So it's actually a very good example of how you can extend the cloud platform to do whatever you want it to do. So currently, I'll try to breeze through 2D and get to the more interesting 3D. So 2D, kind of all primitives are supported with two exceptions, locator and raster. Again, that's something that I'm working on and hopefully get done in the next rather soon. Let's see, come on, open. Directives, again, most of the basic directives just work. There are a few limitations, but again, it's coming along very nicely. As far as wrappers, here currently only things supported are style and tooltip, but again, more things are going to come. And with graphics, if you know anything about graphics, there are millions and millions and millions of options. I don't even know all of them. I don't know. Maybe Lou knows lots of them. I have no idea. But for 2D, a lot of the options are supported. So again, as I alluded to, we have lots more coming. But let me kind of just show you what works. Sorry. So again, it's in kind of experimental, but should shortly be turned on by default. So a very basic example here is graphics in circle. And the easiest way to tell if it's an image or not is to click on it. So we have selection, which should look very similar to desktop Mathematica, and you can resize it. Okay. Here are just a few more examples, again, showing off the support that we currently have. So, including, coloring and opacity and things like that. Including text And as I mentioned earlier, tooltip. So you can see that. We have native tooltip there. And again, it just works. We're working at the box level, so all these things are also supported. So let's see if I can get the tooltip to pop up. Maybe not. So a lot of these things are look very nice. And again, we're working, or at least lots of people working to make this happen. Okay. 3D again works very similar, except it's based on WebGL. So you need a WebGL enabled browser, and at least on Safari or other browsers, even enable it on Mac. So this was a lot of work, and we've actually had this in the cloud platform for about a year now, and it's turned on by default. There are a lot of things supported. There are a lot of things that aren't, because 3D is a huge amount of stuff. But let me just give some examples of that. So again, this was on by default. You didn't need to load anything. If you're noticing that black triangle there should actually be dashed, but that's not 100% supported. But that is running natively in your browser using WebGL. So we have rotation, zoom, and pan. And again, as I said, we're pretty close to having this work inside of manipulate. So instead of image-based manipulates, you'll be able to do a rotation. So here's just demonstrating some opacity and some other things. Let me do at least a cool example, or what I consider a somewhat cool example. So again, because of utilizing the power of the Mathematica graphics language and then basically just converting it into something JavaScript can use, this is very, very powerful. So this is using WebGL. There isn't any reason why you couldn't. I mean, it would take some work, but you could write your own, kind of translation layer to something, some other libraries existing. So I actually use 3JS as kind of a starting point to get to work through this for WebGL. But there we go. And then I'll do one more example, and then we can open it up for some questions. So it's got to load some chemical data stuff first. And we're on Devel, so this is a little slower than it would be on the other things. And let me just rerun it to get rid of that stuff. Oh, I broke it. Okay. All right. So again, that kind of shows you where we're at in getting kind of the more general graphics typesetting, at least. And there we go. It works. Okay. So as John said, it's a rather large project, but we have come a long way. So I guess I'll open it up to questions. That's all we got. Tally. Sorry. So in general, dynamic, the answer to does dynamic work? The answer is no. But certain forms of dynamic do work. As far as how, what are the long-term plans, we would like to support that, but that's something that's going to be particularly hard. So I don't know where that is kind of in the priority list for that. Yes?
In the previous example of this slide,
Mm-hmm.
I was curious how much data goes to before it comes back to that. Do you have an idea?
Okay. So essentially, what's happening is we send just the expression back to the server, and what it sends back is a bunch of JSON, which would be essentially the box representation, generally, maybe some additional stuff. So yes, if you're running a lot of 3D plots or other things, it's gonna up your limit as to what your limits are in terms of resources. So yeah, they can. I mean, it's gonna be similar to you're limited by what are the kernel resources, and then also kind of the upload traffic. There's 2 limits for that. But yes. Yes. So correct. Correct. Yeah. And that's the advantage of interfacing with with a Mathematica package. That's kind of I'm basically saying anything with a graphics head, with a head of graphics, or even at the box level, if it starts with a graphics box, instead of doing the normal evaluation, go through this package. So it just works. Copy the output. That's not possible yet. But the inputs work as you think they would. This doesn't break anything else. So if you make a variable name to say, my plot equals that, it still works as normally. But yeah, output, being able to copy output and represent that as an expression, that's something we're working on.
Okay, hello again. Let's start. For those of you who haven't been here before, my name is Jan Perschko. And now together with Joel Klein, we'll talk about cloud objects and programming interfaces. So if you're asking yourself, what the heck does that mean, then you're probably not alone. But I hope we'll shed some light onto this rather complicated topic. But there are some really nice principles in there. Okay, so let's start by what is the fundamental idea of this? Well, what is the fundamental challenge these things try to address? It's basically you got some Wolfram language code or data, and you want to put it out there into the world. Now, that can mean many different things. It can mean you want to share it with other people that you know. It might mean you have some data that you share across different workspaces. It could mean that you have some device that's connected on the internet. It could be a Raspberry Pi that generates some data, and you need a way to collect the data. Or it might mean you want to create a website or even a whole web application and want to have that powered by a Wolfram language. Or it could mean that you have some large computation and want to outsource that. And the answer to all these challenges is, of course, the cloud. So what is the Wolfram Cloud? At its very core, it's basically storage. So the idea is that with every Wolfram ID, you get some amount of space in the Wolfram Cloud storage. And that's already very useful because it's very tightly integrated into the Wolfram language. So it's easy to save arbitrary documents or expressions in the cloud and retrieve them later. And you can do that either from the cloud platform itself or any of the cloud platforms, or from Desktop Mathematica, and then share it with anybody who has access to the internet. But then on top of this space storage principle, there is a very scalable on-demand computing infrastructure. So the idea is that everything in that cloud is at the same time evaluatable. So you can do computations in this cloud. That makes it a very active one. So at the very least, this is a computable storage and hosting solution at the same time. And computable means both accessible from computations, but at the same time being able to do computations in the cloud. That makes it very nice. So how does that actually work? One fundamental principle is that everything that's in the cloud, in your space in the Wolfram Cloud, is accessible through a cloud object. That's basically a handle to something in the cloud. And one principle is that everything in that cloud has a unique identifier. So if I just do this, and I'm already authenticated, otherwise you would ask me for my password to log in. But now I'm already there, so by creating such a cloud object, I get a new URL that contains this long ID here. The interesting aspect of this is probably that by the magic of probabilities, we don't even have to make a trip to the server to generate these IDs. They can be just generated randomly, and there's a very, very low chance that they will ever collide. So you can just generate IDs and put something there later. And that's exactly what we want to do right now. So let's create a test file on my local system, and then we can just use the copy file function as usual with the cloud object as a second argument. So this will copy the local file into the cloud. It just works. If I click that file now, or that link, and it's nice that it is a link in Mathematica, we make use of interpretation boxes and all these things. So you can see this is now a usual URL in the browser, and I just have that content over there. And anybody could access it as long as I give them permissions. Of course, that also works in the other way around. So I can copy the file back to my local file system, read it in, and it has the same contents, of course. So that's a very low-level aspect of it. Then there are other file system-like functions in Mathematica that all work seamlessly with cloud objects. So it's a whole family of put, save, and get. So if you do a put on a cloud object, it will just create a new cloud object and put this arbitrary expression there. There is also a shortcut that does exactly that, so that you don't have to type this all the time. There's cloud put, which takes an arbitrary expression and produces a cloud object with that expression. If we want to get it back, that's what it does. And this is an ordinary Mathematica expression again. Same for export and import. So if we have some image, then we can export it to the cloud. So if I execute this, I get this link. And here you can see some slight variation. So I didn't use just cloud object bracket bracket, but now I gave it a name. And this is literally a directory and a file name. So that has consequences for the URL. So if I click that URL, you can see it's back there. And of course, it is just image. And this is sort of my user ID. Again, it's a UUID, such a long identifier that represents me on the cloud. But the nice thing is you will be able to register vanity names in that cloud. And so for me, that would be J. Pershko. So now I get that nice URL where I can access any object that I put into my cloud. And at the same time, if I go now to the cloud platform, that means that here under my files, there is now a directory world, and it has the file in it. And I can just open it here. That all happened from this one Wolfram language call. Of course, I can get it back the same way using import, and there it is again. Now, one thing that's almost magical already is you can take your notebook that you're currently working with and just put it into the cloud by using export of evaluation notebook. So it creates this cloud object. I can click on the link, and it will open in the cloud platform, and I can go on and edit it over here if I want to. Now you can see it has all this framing around it. That's because I'm logged in and I have access to it in that way. If you were to share that notebook with someone else, you could do the same thing. You just export your notebook to the cloud, and if they access it and don't have the subscription to the programming cloud or something like that, then they would not see all the framing, but they would still see the notebook, of course in a read-only mode, but they could see your documents and maybe even interact with them. So that's a very nice way to export interactive content with other people and share it. Okay. So next is cloud computation. If we have this storage, and now we make it active. At the very core, there is cloud evaluate. It just takes an arbitrary expression and uses the cloud servers to actually execute it. So as a very simple demo, we'll just use the machine ID here. So, yeah, and it works. So to compare that with my local machine ID, it sort of proves that this was actually evaluated in the cloud. Of course, you can do arbitrary computations that you could do with Mathematica. So if you create that graph, it will just evaluate in the cloud and come back as a nice graphic. That by itself is maybe not that impressive enough, but if you think about having thousands of kernels that run in the cloud and that you can access just by typing in something like this on demand, that's really useful. Not only kernels, but also, let's say, some GPUs that run in the cloud, and you get access to that completely seamlessly. Another useful shortcut on the language level is a cloud function. So let's say you already have something in the cloud, a cloud object that contains a function, a pure function like this. Then by just wrapping cloud function around it, it will become an expression that when you apply it to arguments, evaluates in the cloud. You can either supply it a cloud object or some pure function. Yeah. Oh. I guess you can't see that somewhere down there. Yeah. Okay. Right. So that's. You have a question?
Is cloud evaluate always blocking?
That's a good question. Very good question. So yes, the idea is that cloud evaluate is blocking. We don't have it yet, but we'll definitely have cloud evaluate asynchronous. So that would work in a way where you give it an expression, it evaluates in the cloud, and you also give it a callback function that gets called as soon as the result is ready.
Why wouldn't it be an asynchronous task? Because we already have all of that stuff, asynchronous tasks.
It should certainly be related. Yeah, absolutely. I mean, even if you don't have that, the fact that cloud objects are so nicely integrated into the language almost make that unnecessary, because what you can do in your evaluation at the very end, you just assign it. You assign the result of your computation to a cloud object, and that's what you access when it's ready, right? But yeah, we definitely need such an asynchronous mechanism. Okay, so that's basically the use case where you have some evaluation that you want to outsource. Now there's this whole other story where you have some algorithm that you want to share with the world and you would want others to execute. And that's where API functions come into play. So when we say API in this case, we don't really mean an API that we provide to you, but we give you a way to create your own APIs. And at the very core, that on the language level, that's what this API function is about. So what this means is when you want to share something that's accessible through a RESTful HTTP interface, you usually need named arguments, right? There's a URL, and then you say $x equals something, if you're familiar with these things. What we need on the language level to support that is a function that takes named arguments. And that's exactly what this API function is. So it basically says it is much like a pure function that has a body and some formal parameters, but instead of using these things as positional arguments, they have external names. They could be the same, just for illustration purposes, they're not here. So that means I have a function that takes a parameter a. And now I can apply that by saying, I apply it to a list of rules where a is assigned something. Of course, that will work in the upcoming version of Mathematica with associations as well. So now you have this thing that's maybe already useful in the local kernel itself, but the real useful thing happens now.
What is
okay.
can you type my API so we can see what it is?
It stays the same. It's just this. We might provide some nice looking thing about it, but
it's local.
Everything's local, yeah. That happened locally. Now, one way to make it non-local is, of course, to wrap a cloud function around it. But even the more interesting thing is to deploy that API function so that everybody can execute. And that's what cloud deploy is about. So you say cloud deploy of this API, and again, like always, you get back a cloud object with this link. If I click it, I will get back failed because I didn't supply the necessary argument. So it has a required parameter a, but as soon as I do that in the browser, right in the URL, I get back the result. So, and that could be executed by anybody now, right? And not only people even, but machines, other algorithms, other programs in other programming languages can use such an API to integrate highly sophisticated Wolfram language computations into their area. For this particular use case, it's probably not so suitable to use images like we do here. That's nicer for humans, but if if you want it machine readable, then there's a result format text, for example, and you will just get back the. It's an interesting question. It wouldn't be crazy to do that, of course. I mean, one thing that's useful about this is that, I mean, it not only has the feature of named arguments, but it identifies something that you want to be an API. So the idea is I put something on the cloud, and just by the matter of what it is, what expression it is, the cloud knows what to do with it. And so we need some special form of expression that says, execute this when you access it. Okay? So the idea would certainly be that as an argument to cloud evaluate, or as an option, you could say use that many kernels or up to that many kernels. And if you have something that facilitates parallel, then yes.
If we had a task or something we needed to accomplish where it's only valid for some period of time, is there a way to say, I need this accomplished within this period of time, or don't do it, or something to that extent, or only dedicate, a certain amount of resources?
We don't.
From a real-time perspective, is there any way to solve problems that have a very narrow window of value?
We don't. Right. Yeah. I mean, I'm not sure if that solves all the problems, but that's an interesting point. Absolutely, we take that into account. And I mean, all of you are very welcome to share your ideas how this should work, because it's not completely done yet. So definitely open to suggestions.
Also want a dollar constraint.
Absolutely, yes. Absolutely.
Basically the same question.
Yes. Yes, absolutely. So especially for an API function, when you deploy it, you will be able to say, I don't, we don't have it yet, but there will be something max time per request goes to something, and things like that. Right. And very good point. Yes, maybe we will almost out of time. But so what you can do here is it is a bit more evolved. So you can do typed arguments. You can say this is an integer or an expression or whatever. And then as a third thing here, I can specify a default value. So if I say the default value of this is 2, then I should be able to execute it like this.
But there's no way to have like the richness of down values.
Oh, down.
Something like where you have a whole pattern matching language. So if it's an integer to something, if it's real to something else.
That would not work for API functions in this sense. No. They are meant to be the front door entrance to your complicated computations, right? So they rather mimic the rather simple HTTP RESTful level by supplying named arguments. But of course, you're free to do whatever you want behind this door, so to say.
The full definitions, when you do cloud deploy, the API function called the function G, and G was defined elsewhere. Would it pull the definition?
Yes, that's what Cloud Deploy does. So basically, Cloud Deploy does two things. It figures out the type of the expression you give it and does some corresponding stuff. And it also pulls in depending definitions. So maybe it's a bit too long to show this now, but yes, it does. It uses language extended full definition. If you want. Okay.
If I've understood it correctly, is that you could quite easily just put a function one stage behind this
Absolutely, yes.
would do all that filtering and kind of conditional responses to
Mm-hmm.
patterns of arguments. Have I got that right? That you could make this a very kind of thin protocol,
Yes.
which is something immediately quite complicated.
Yes, so you should be able to do something like this, right? And now, if we deploy this thing, you can actually look at it.
That can be as complicated as you like.
Absolutely, absolutely. I mean, the F can use all sorts of pattern matching or whatever. Now, if you do an import on this API and we look at it in text form. Oh. Hold on a second. Oh, yeah, sorry. Absolutely. I think it's 60. So there you can see in the cloud object itself, that's what it stored. It stored the definition of F along with the API function expression itself. Any other questions right now? Okay.
Okay, let's say that I have a manipulator
Mm-hmm.
that I've done, and I get also a blog, maybe WordPress or whatever,
Mm-hmm.
like to publish it with some kind, and have it, publish it with some, all the stuff that we have seen before, like balance and other things. You can do that. There is a way to embed a manipulate inside my WordPress or whatever else.
Yes.
Or something.
It wouldn't work right now, but it would basically use the very same mechanism that notebooks use already. So you saw you could cloud deploy or export a notebook, and if you do that with a manipulate, it would do the exact same thing. It would deploy something to the web, and when you access it, it's rendered using our whole stack of what we do in the cloud platform. So by the way, that's also why all this work we're doing for the cloud platform is really important for everything like this too. Everything we do with graphics, with manipulates, has a really high impact on this too, because that means you can share your manipulates, share your 3D graphics, and the end user doesn't have to have any plugin or whatever. Mm-hmm.
How does the user, I didn't understand, how does the user find and download what you put out there?
Right, so that obviously wouldn't work by chance with these long URLs, right? So that's where these vanity URLs come into play. I mean, they would still not find it, but that's probably what you would share with others, and you would say, here, I have this API under this nice URL, and go use that. If you're thinking about a real exploration system, that's in the plannings too. So the idea is to have sort of a Wolfram hub where all these cloud objects come together, and people can see what's going on there and see, okay, that's interesting. I want to use that cloud object.
No, that's only for directed sharing. It's not that somebody, so I say, I have programmed the PDF and now I want to put it on the internet. Right?
I mean, you still have to have a web page where it actually lives, right? I mean, you could either have it to have the manipulated by itself and it has a nice URL, or you embed it into another blog. But you can definitely do that, yeah.
But eventually we'll have sites hosted on our technology, right? Entire websites.
Right, yeah. I mean, you could imagine a notebook being a website already. Another thing, I mean, we're really running out of time here. Yeah, maybe we should show some examples.
There's just one example that's relevant here. What's your browser? On your browser. So I've taken some of these examples and put them on an internal WordPress blog that I just use for my own engineering notes. Where's my blog? You have that?
Then you debug it, and when you deploy it again, you get a different code. Is there a way to get the same code so that I do not lose my link to your app?
Right, so you could either use the same code again, right? You store the reference to that cloud object and use the same UUID. That would work. You can overwrite cloud objects. But the preferred way would probably be to use these vanity URLs, where you give it a name, and that's an explicit name in your cloud storage. And at the same time, you have a nice URL for the root of your cloud storage, so to say.
Would versioning be up to us then?
No. Versioning works already, and it's integrated quite deeply into the cloud. Okay.
Gotten most of the major points, and I just wanted to demo a couple of things. This is just a WordPress page that I wrote up quickly, and I can see that I have a broken image link for some reason. I've included in my post a link to what we're calling an instant web form. This was created through a GUI, and you could create it through a cloud deploy of, I think, form function. So a cloud deploy of form function could create one of these things. It's similar to a manipulate, but it's intended to be used in a web context. So this is just a front end onto a simple calculation that I'd written. And it just generates a handy table. This is a flash photography thing. So this is a quick demonstration of, we had something, we wanted to get it in the hands of people. Manipulate is great as a document if you're sharing a document, but if you wanted to kind of embed something in another web environment, this would be a good way to do that. And over on the side here, this image this is being generated from PHP code in the theme for the WordPress blog, and it's an image tag who's referencing our cloud and actually calling an API function. So this is a different way to show that kind of this web access is kind of giving us a universal way to access Wolfram language stuff, to get your stuff out here, which is the point Jan was making. So I think we'll leave it there unless there are any more questions. Okay, good. Thank you.